everybody then. I'll make a start. Can you hear me at the back okay? Can you hear me? Yeah, all right. So firstly I should introduce myself. My name is John Waltho. I'm actually Professor of Biophysics and we're an NMR group primarily. But my part of this course is to give you an introduction to the basics of chemical kinetics. This is a subject that pervades an awful lot of chemistry. It's incredibly useful in all sorts of different circumstances. Before I go on to the lecture material itself, I just wanted to draw your attention to Blackboard. You're all, of course, familiar with the Blackboard pages and the recommended text on those, but I'm just going to mention those again later. But for the kinetics part, down here, most of you, of course, will have found the lectures that I'm about to give. But I specifically wanted to draw your attention to this folder down here. By the way, the revision lecture slides, this is a revision lecture that occurs just before the exam that Gareth organises. But down in this section, there's a few help me files, so one Greek alphabet, Greek letters, of course, get used a lot in chemistry. Basic mathematics that you might need to know that underpin what I'm going to talk about. Then the third one is this revision overview guide. So this is basically a lookup, it's like 2 pages of lookup of what the principally important aspects of what I'm going to teach are. And down below that there are some sample questions. There's between 40 and 50 questions in here. These are all bona fide or previous exam questions. So I think if you work through those, it will give you an idea, a very accurate idea of what kind of things typically get asked in this part of the module. So hopefully there won't be any surprises, excuse me, come May. I've already uploaded the answers to those questions here. Probably best to have a look at them, doing them before you read the answers, but different people work in different ways, so of course I'm very comfortable with however you want to deal with this. There was a few gremlins in these model answers. I think we've found them all, but there may be 1 or 2 others. If you do find any oddities, do let me know and I'll sort it out. And then finally, this file at the bottom, this is some relevant derivations. So I'm not going to go through the maths of various derivations of the equations I show you. It won't take too long. But if you want to read them, where they come from, specifically if you're of a mathematical bent, you like that approach to chemistry, then they're all in here, and by all means have a look at them. Because they're in here, of course, I'm never going to ask you in an exam question to do any of these derivations. That would be unreasonable. But often people like to know the fundamentals of where these things come from. And in there, there's the integrated rate equations, there's enzyme catalysis, some of the mechanisms that I'll show you in the final lecture, those kind of things. So there's a lot of resources on Blackboard, do try and use them. There are also some multiple choice questions that will come up at some point. Right, so on to the lecture material itself. Right. So in this lecture, I'm essentially going to give you a general overview of kinetics. A lot of this will actually be revision for most of you, but we have to cover this for those of you that haven't come across this material before. I'm going to talk a little bit about stoichiometry and how stoichiometry relates to kinetic processes, defining actually what a reaction rate is, what it is that you want to measure, and then finally how you measure reaction rates. I'm going to cover that for a little bit of lecture. And then finally, the first 5 of my 6 lectures, all of them have a workshop at the end of it, so my lecture will only be 25 minutes or so long, maybe half an hour long. Then there'll be a workshop question that I would like you to have a go at, and then we'll go through the answers. So, today's workshop is a very simple one about obtaining a reaction rate on the basis of some experimental data. Just to give you a heads up for the course as a whole, or this part of the course as a whole, I've talked about today reaction rate, stoichiometry, etc. Tomorrow I'm going to look at general rate laws, where they come from, what they do, about the orders of reactions, and then I'm going to introduce you to this initial rate method to try and work out the order of a reaction. And next week we're going to look at integrated rate equations and how you use those, half-lives and where they come from and what they tell you. And I'm going to focus on zeroth, first and second order reactions. If you wish, you can extend it to more complicated reactions. The principles are all the same. The second lecture next week, I'm going to talk about the isolation method, which is a way of simplifying higher order reactions into more straightforward ones. And then I'm going to look at some of the complexities that you can get, like parallel reactions or consecutive reactions, and how that leads into understanding what the rate determining step of a reaction is, and this thing called the steady state approximation, which is a fantastically valuable way of analysing quite complicated reactions. Then the final week, we're going to boil things down to the elementary reactions and look at mechanisms, because that's really where a lot of kinetics is focused. Concepts like molecularity, looking at relaxation methods, and then also look at the temperature dependence of reactions and what that tells you about the species that are involved. And then finally, I'm going to look at energy profiles and energy surfaces and how they define what's going on in all these reactions. This concept of transition states, and then look at this in the context of catalysis by all sorts of materials, including enzymes. So that's where this whole part of the module is going. Let's start back at the beginning. So most of this stuff I'm going to teach you, certainly in the first 4 lectures, is readily available in every every chemistry textbook that is based at college level and above. So these are the 3 that we recommend you have a look at, but if you look at any of them, they will cover this material. And this slide is just to remind you of a couple of things. So there will be practical exercises, so please bring a calculator with you to the lectures so you can have a go at that. And finally, the office hours actually are after the Tuesday's lectures up in the MIB. So I work in the MIB. If you don't know where that is, it's on North Campus, just under the Mancunian Way. So if you want to talk about things in more detail, we can either do it after the lecture or back up in the MIB. Okay, the other things that it's useful for you to know is that this builds on a lot of the elements that you've learned so far to do with the mathematical and practical parts of the course. So it will call on elements of plotting graphs. Kinetics necessarily uses exponentials, and therefore you need to use logs. Rate equations are essentially differential equations, so you need to know about differentiation and integration. Though specifically, as I said earlier, those aspects are not going to be examined on this module. But to understand it properly, you need to be aware of those processes. And so these cross-references should work with your maths module. Right, enough of the background. Let's get on with the kinetics itself. So chemical kinetics, as you probably already know, is really this process of studying the rates of the whole multitude of chemical reactions that are relevant to your particular study. And one of the reasons, well, people study this for 2 reasons, basically. One is to try to understand the mechanisms of the processes that they need to use. And the other is to try to make these processes go in the direction that they want them to go, as opposed to the direction that your current set of conditions determines will lead to which determined outcome. So mechanism requires you understanding all the component steps, or the elementary steps as they're formally called. And to understand this, you need to break down complicated reactions into very simple processes. So I'm going to look at this the other way around, look at simple processes and then build it up to a complex reaction. And if you think about what you can measure to look at the rate of a reaction, of course you can measure the rate of consumption of the reactants, or the rate of formation of the products. And they should give you the same answer, obviously, if the reaction that's going on is the one that you think is going on. And there are all sorts of physical things and chemical things that interfere with that or modulate that. So you may also want to look at, for instance, the effect of temperature and what that tells you about a reaction, or the effect of pressure, or as I said earlier, the effect of catalysis, which is one of the principal areas of chemistry research currently. So the questions then, very simple questions that you can address, things like what are the reactants? It's amazing how often you would look at, and you would draw into chemical reaction, you would try and do it, and you would find out the reactants are not exactly those that you thought. So secondly, does it form the desired products? This is a major outcome, of course, because very often in chemistry you're trying to make something, and you're trying to make something in high yield, and so all the alternative things that can be made with those reagents matter. So if you can speed up the rate of making the product you want, then of course that's going to make the whole process massively efficient. This is the entire domain of development chemistry in the pharmaceutical industry, for example. So I talked about different conditions, so temperature, pressure, whatever, and catalysis, and how inhibition can help you drive a reaction in one way or another. But I just wanted to point out this final thing, that the principles are very common, or they are common across all of these processes. And so it doesn't matter, I'm going to talk about chemical reactions almost exclusively. But it also applies to things like radioactivity, which is probably an example you've seen from school. Things like diffusion, so movement through liquids or through gases. Phase changes, which are a big part, of course, of all sorts of processes. Binding. Again, principle of the pharmaceutical industry, conformational change, how proteins and molecules are influenced, but also lots of general things. Yeah, so the weather, how traffic moves, economic growth, population growth, all sorts of things are controlled by these fundamental processes of kinetics. So even if you end up not being a chemist at the end of all of this, hopefully that's not true, but of course it does happen, then the principles of kinetics will be something hopefully you can take into your future career. Right, but let's focus on the chemicals for the moment. So one of course the tricky things that you have to deal with in terms of all chemical reactions is stoichiometry. You have to write balanced equations, and therefore the stoichiometry matters. So if we look at this very simple decomposition reaction here of N2O5, when we balance it properly, then you need two N2O5 molecules to make two nitrogen dioxide and one oxygen molecule. And we need to know this balanced equation so that we can measure the rate so that it's common whether we look at the rate of decomposition of N2O5 or the rate of production of NO2, or the rate of production of oxygen. This final note on here is just to remind you again that, of course, these reactions also have thermodynamic components, as John Agger's just been telling you about. So if they're exothermic or endothermic, and of course you need to keep a very tight control on the temperature, otherwise the reaction conditions change and the rate you measure then is inappropriate. So how do we take this into account? Well, that's because we define the rate of reaction then to reflect the number of moles of reaction per unit time, not necessarily the number of moles of reagent, the specific reagent that's changing. So if you look at this reaction then, the rate of this reaction is defined as half the rate of the decrease of N2O5, or a quarter of the rate of the increase of NO2, or the rate of increase of oxygen. So if we write that simply as a differential, there's my mouse here, So instead of looking at the rate of change of the nitrogen of the N2O5, then you need to take half of it. This is a rate of loss, so it's a negative sign, of course, on the differential. This is a rate of production, so it's a positive sign, but we need to take a quarter of the rate of production of NO2. Or we can simply look at the rate of production of oxygen. All of those measurements, corrected by all of those factors, will give us exactly the same number for this rate. So this is how you get the number of moles of reaction that occur per unit time. Consequently, then, rates are expressed in moles per decimeter cubed per second. So, generic concentration as a function of time. And final, just a reminder that you should be able to get it from looking at reactants with products. So let's look at an example where we've got a concentration of reactant and it's dropping as a function of time, and it's got this particular relationship. So we can measure the rate at any point in this reaction, but of course it will be different if we measure it here, or we measure it here, or we measure it here. And so wherever we measure it, it's called an instantaneous rate because it's the rate that's appropriate at that instance of time. But we have to bear in mind that this is a changing phenomenon as the reaction goes on. And so I've highlighted this thing called the initial rate here because it turns out, as I'll explain tomorrow, that the initial rate is really very valuable in trying to understand things about the reaction, particularly the orders of the reaction. But you can probably see an issue here, and that is that if you're trying to record this experimentally, of course, but if it takes you from 0 time when you want to start, this long, to actually start recording the data, then of course you won't see the initial rate. You'll have to extrapolate back to it. And to extrapolate back to it, you need to know the form of the rest of the time dependence. Otherwise your extrapolation will be wrong. And if you start off from there and think, well, that's my initial rate from there, you'll also be wrong because it won't be steep enough. So then there's this fundamental factor always between how fast I can start my reaction versus how fast does the reaction go. So ideally, the reaction is slow compared to the amount of time it takes you to start it. I'll show you some examples at the end of today how we can minimize that as a problem. That then brings me on to these issues, which is how do you deal with chemical reactions that can range in timescales from femtoseconds, so 10 to the minus 15 seconds, so things like photosynthesis, first steps of photosynthesis are that fast, to billions of years. So one of the enzymes we work on, if the enzyme wasn't there, the reaction to turn over once would take many multitudes of the time that the universe has currently existed to happen. Now, of course, that's not something that is experimentally accessible, but it makes the point that the spread of reactions that which you're interested in can be phenomenally large. So how do you do it? How do you deal with such different timescales? Well, let's look at what you might classify as slow reactions. So those that take more than 100 seconds for things to change markedly. So then you can use things that are called sampling methods. This is just a posh name for saying, well, I start my reaction, and after a certain amount of time, I'm going to take something out, and I'm going to do something with it to measure how much of my reactant or product I've got. So in that sense, it's called a discontinuous measurement because you just take stuff out and you measure it. And the things you need to be wary of if you're doing this kind of measurement of rates is that the time it takes for you to measure stuff after you take it out, you want your reaction to be slowed down during that process, preferably not doing anything. So quite often then people use quenching methods, and they can be, for instance, cooling. If your reactions occur at a certain temperature, you can cool it right down, so you can put it in ice, you can put it in a freezer, you can put it in liquid nitrogen, depending upon the temperature drop you want. Or you can dilute it if the reaction is dependent upon molecules coming together. Or you could add an agent, so that you could add acid or water or something that would just stop the reaction completely. So there's a multitude of ways in which you can take out your samples, measure the concentration of species as a function of time, as long as your reaction is slow enough for you to do that. The alternative to this is you just measure it in real time. And quite often this relies upon some kind of spectroscopy. So Gareth's going to teach you about spectroscopy. I don't know if it's next or last in this module. Some spectroscopies. But again, there is a whole variety of spectroscopies you can use that report on the concentration of species. And so then if you do your reaction within your spectrophotometer, spectrometer I should say, or you take your sample out and put it into your spectrometer, you can follow things in real time. Actually taking it out isn't in real time. So if you do a reaction in your spectrometer, then you can follow it in real time. And that actually makes your data a lot less prone to error. But as I've sort of said several times now, there is a whole multitude and massive variety of ways in which you can measure rates. And so this slide here is really to make you aware of some of that broader range. And these are quite often used in practical class, so this is sort of a useful series of reaction methods to know about. So this is just a list where you change physical conditions, well, most of them are. So for instance, if you change the pressure in a reaction, so if your reaction like that decomposition of N2O5, you get a different number of moles of products than you do of reactants, therefore that gas will change, the pressure will change. You can measure that simply by having something like a manometer attached to your apparatus. You can look at the change in volume in a reaction, so again, you're producing more species, the volume will change. So using a dilatometer as part of your measurement system. If your reaction involves gas evolution, you can capture that in a burette, and just measure the volume of gas as it increases during a reaction, or indeed decreases. If you change the number of ions or the nature of those ions, you can change the conductivity. So if you do this in a conductivity cell, this reaction, you'll just be able to measure that conductivity change as a function of time. And you don't have to be restricted to electrical conductivity. You can measure thermal conductivity using this thing called a calorimeter. And then you can look at the interaction of molecules with light or any electromagnetic radiation frequency that gives a response in your molecule. So for instance, you can look at the polarity of light as it travels through your sample. So if you've got a chiral sample, it will rotate plane polarized light. if the nature of the chromophore, the chirality around the chromophore changes, then that rotation angle will change. So you could do your reaction in the middle of the polarimeter, and you would see that process happening. Or you can do more standard spectroscopy, some absorbance spectroscopy or magnetic resonance spectroscopy or whatever, and that will change as your molecules change in a reaction. So the final thing I was going to talk about before we go into the workshop part was how do you deal with reactions that are faster than 100 seconds in time scale. So you can get mixing devices that allow you to mix things much faster. So for instance, in some of the spectrophotometers talked about, you could mix things probably in seconds. But if you want to get to faster timescales than that, I'm just going to go through two sets of apparatus that would allow you to do that. So the first one is called a stop flow, or its variation, a continuous flow spectrometer. And it's a very simple thing, actually. You can build this with syringes and tubing of your own. But the process is that you'll put your two reactants into two syringes, as shown on the left-hand side here. And the tube that comes out of those syringes comes into two sides of what's called a mixing chamber, so just a vessel. And there's a third input, or indeed output, to that vessel, to which a tube is attached that connects to another syringe called a collection syringe. So the way you start this reaction is, as I was saying, you fill your two drive syringes here with your reagents, and you push your collection syringe in because there's nothing in it. And then you use a thing called a stepping motor, so a motor that's very well controlled in terms of its timescale of its pushing. And what it does is it pushes the two syringes in, which means that liquid comes out of both those tubes. Sorry. Liquid comes through both this tube and this tube into the chamber. The reaction starts, continues as it flows down this chamber, and then it pushes this plunger from its in position to the out position. And then you have your detection system, like your spectrophotometer, placed close to your mixing chamber, and it tells you the nature of the molecules, the reaction, as they pass that point. So when this syringe on the right-hand side stops, then the spectrophotometer simply measures aging, because the flow stops then. It just measures the aging of the reagents in that part of the tube. So the useful thing about this apparatus is that this mixing process in here can take a matter of a millisecond. In some very sophisticated devices, even a fraction of a millisecond. So you can look at reactions then that occur at 10 to the 3 per second or 10 to the 2 per second relatively straightforwardly. Whereas if you had to mix it on the bench and put it in your spectrophotometer, you can only measure things about 10 to the minus 1 per second. So you're 3 orders of magnitude slower. There is a variation of this called the continuous flow apparatus. So then you don't have the collection syringe, you just keep pouring your reagents down this tube, and you move your spectrophotometer along the tube, and that tells you the behavior of things at different ages, because time zero is when they meet in the mixing chamber. The disadvantage of that is that you need tons and tons and tons of reagent, because you're pouring it into a bucket at this end. So that's not used so often, but it can actually give you even better time resolution than a stop flow device. But there is this fundamental issue that mixing takes that period of time. If you try and mix things faster than that, liquids faster than that, then you tend to get separation of those liquids. And so, if your reaction has to start by mixing two things together, you really are stuck at this millisecond timescale. If you want to look at faster timescales than that, people tend to switch to things like photolysis. So of course when you shine UV or indeed X-ray light at a bond, you can break that bond into two radicals. That process occurs at femtosecond timescales. So if that starts your reaction, then you can truly look at things that are that fast. And the way that you would do that, so here's a simple piece of apparatus. I think this is one that's in the third year lab. In some of the project work, you might get to use this. So essentially you have these flash tubes and they just output high energy light around your sample, and then you start, you switch them on, which you do very quickly. They irradiate the sample, that starts the whole reaction process. Then you can follow it with a spectrophotometer, so you do this in a spectrophotometer, so the light source is just a bulb, so you just look at the absorbance or fluorescence or whatever, the sample in your spectrophotometer. Latterly, people tend to do this instead of with flash tubes, you can do it with lasers, because these you can gauge and control massively accurately. And so as it says, you can shine a pulse, a femtosecond pulse, onto your sample. If it breaks the bond, that starts the reaction. Then you can follow processes that are on the order of a picosecond or slow. And I'll show you an example actually tomorrow of this kind of chemistry in action. Right, so that's all I'm going to cover as far as today's lecture is concerned. So now I'm going to switch to the workshop example. As I said, it's a very simple example today, but I think it does illustrate some key points that I want to make sure you're aware of. So the question is, given this reaction between hydrogen peroxide and iodide to produce I3 minus, these are the concentrations of iodide as a function of time in minutes. And I simply want you to find the rate of this reaction. Okay, anyone want any more time? Or shall I just go through? I take it that's a no. Okay. Okay, can I just go through the answer with you then? So here's an answer I've seen. It's not here today. That answer is wrong in lots of ways. And the advantage of doing this in a workshop is so that everyone's very clear as to what is right and what is wrong about answers, just so that you can be precise. Being a scientist, there's actually a lot about being precise about things. So what's wrong with this answer? So first of all, I asked you to, well, the question says find the rate of a reaction. A rate of reaction is never negative. The slope is negative, but the rate of reaction isn't. This is a reactant in this reaction, and so the rate equation involves minus dr dt. So the minus sign goes. Three other things are wrong about this answer. One. There's no units, exactly. So there's no units in this reaction, in this answer. So that is equally right with every other number that you could write on the page. If there's no units, every number is equally right. Because of course you can define your units to make that number right. So if you don't include your units, your answer is by default wrong, because you may as well have written infinity. Okay, so please be very wary of that. Units, absolutely crucial. A couple of other things wrong about it. Did everyone get this answer then? Okay. So I think you should probably spot one of the things that's wrong about it. Yeah? Perfect. So, this has got 6 significant figures in it, and yet you're fitting data that are not falling precisely on a line. So this is massively over-precise. You're telling the reader of this a number which you cannot defend. So this lot can all go. Final thing. Well, 2 other things actually. So the units this is in, if you've done it like this, it's moles per decimeter cubed per minute. Question obviously wants you to convert this to seconds. But please be careful with your questions. Seconds, of course, is an SI unit, minutes is not. So very often, if you're approaching a rate constant or a rate, please convert it to seconds. So the other thing is that the stoichiometry is not taken into account with that answer. So you need to divide it by 3, because in the stoichiometry of iodide in this reaction is 3. So if you look at the bottom, So this was the number I was just talking about. So the rate of change of iodide is minus 4.2 times 10 to the minus 4 moles per decimeter cube per minute. The rate of reaction, you need to account for the stoichiometry and the minus sign because it's a reactant, not a product, so it goes away. And so you would come up with an answer was about 1.4 times 10 to the minus 4 moles per decimeter cube per minute, and then you need to convert that to seconds. So I want to say one other thing about this. Because you find that some people would then go back, okay, so they fit the line and say, well, okay, it fits the line pretty well. Let's get a gradient from the difference of two of these numbers. So the problem with that approach is that the data don't fall on the line. So if you want the slope of this line, you have to take where the line is present, not where the data is present. So for instance, here it's crossing x equals 0 on the graph, so that's one point you can define. And here where it intercepts the x-axis is another point that you can define, and so that's the number that are used here. So not the data points, because the data points are not on the line, but points that define the line. So please bear that in mind when you're calculating the gradients of lines. Look through previous exams, gradients of lines come up in almost every one. This is something it's almost inevitable you will be doing in an exam. So please bear in mind that that's how you need to measure the slope of these lines. Significant figures is a bit of a harder one to judge, because really what you should do to get the significant figures is that you should have some measure of the distribution of the points away from the line, and that is algorithmically something that would take you too long to do in an exam question. So you kind of have to estimate it. The best way to estimate it, if you wish to be as accurate as possible about it, is draw multiple lines through these data, say what is a reasonable biggest slope and what is a reasonable smallest slope through here. What numbers do I come up with for those, and that will give you a range to estimate your error. People don't do that in exams. Do that in exams. But if you're concerned about the number of significant figures that you're quoting, that's the thing you should do. Great. Okay. So thanks everyone for coming. See you tomorrow, where we're going to talk about reaction orders. Would like us to vacate quickly for the next.
Oh yeah, your simplifications, 0.8 in your working, and the answer is 0.3.
So that was that's a data point,
Yeah.
as opposed to very comprehensive.
Oh, so you plotted it and then. Sorry.
That's what I was trying to explain about the line.
Right.
The line.
So in the exam, that would be good. Graph paper or something. Right. Okay. So you actually have to plot things. That's fine.
It's a very crucial point. So I'm very glad you asked it.
Yeah. It just threw me off a second. I understand that the precision was so when you drew a line of best fit, you were just eyeballing it basically in drawing the line of best fit.
To be honest, I didn't draw that. Years old last night.
But I mean, in the exam you'll be eyeballing it and going, what's a line that is for this?
And tolerance will be given for whatever I call it off.
Yeah.
On the goal mark, when you know what to do. So if your values, outline.
Yeah, it's the practice you just do in the Excel.
So if you're doing temporal dependence, it might be out by 2 orders of magnitude. It's still
Yeah.
right.
Yeah. Okay. Because in practice you just do like least square fitting in a.
Yeah. So I imagine that was done in Excel.
Yeah.
And those numbers were what Excel gave you.
Okay. Cool. Thanks.
Is that right?
Thanks.
Good. Was it clear?
Yeah, it was pretty clear. I particularly like the workshop format with the question at the end. Dr. Agger was, he tended to do a lot of derivations, and I know some derivations for thermodynamics are included in the exam, so it's more relevant.
Yeah.
And we tended to sort of follow along a lot more, but having a sort of worked example like this, I think is very helpful.
I think if you look at the questions,
Yeah.
then you'll get confident and comfortable with the kind of things.
Yeah, no, I know. And I'm still, and I am, and I know we're supposed to be teaching ourselves to a great degree, but it's still helpful to go through it. Because something like that, I would have gone, it might have, might have just not quite gone in.
It's trying to get over best practice of doing things, because some people would do things slightly wrong, and you lose a mark. And this question has 25 marks in it, and you have to take a mark off because someone doesn't put the units on. It's really frustrating as a marker, because you know that the person knows what they're doing.
I know. Nobody's got here without knowing what units are. It really wouldn't take long to do a kind of, depending on how many data points you've got, for 5 data points to do least squares or something like that.
Oh, to do it longhand?
Yeah, I think so.
That would be heroic.
But, no, if you have a calculator,
Yeah.
I don't think so.
Yeah. You're right. I mean, yeah.
Do you ever set questions like that? Or not? I suppose
You'd have to calculate the sum of the squares.
No.
Someone might. I don't know what happens in that sort of data handling